Hello. Is the sound is good? All right. Please let me know that you hear me.
Yeah, it's fine.
Thank you very much. Okay, let's begin. I will show the tasks. Okay. Here they are. And as usual, uh, I'll give you the link to our board. This is the link to the board. And we begin with ordering at the set of monomials. The most popular ordering is lexicography ordering. Let me remind what is this. We have two monomials. For example, we have n variables, t1 and so on, t n. This is variables. We consider polynomials from in these n variables, t1, tn. And first of all, we consider not polynomial, but just a monomial. Monomial is t1 in power alpha 1 multiplied by so on tn in power alpha n. And let me denote this monomial as, for example, L. We have other monomial, t1 in the power beta 1, and so on, tn in the power beta n. And this, let it be the monomial S. And I want to say if L bigger than S or S bigger than L, or they are equal. Okay, I say that I fix the ordering of my variables. For example, I consider lex t1 and so on tn. And then I try to say, if I say that if alpha 1 bigger than beta 1, then L is bigger than S. And it does not depends on other alpha and beta. So if alpha 1 is bigger than beta 1, then L is bigger than S. So if alpha 1 smaller than beta 1, then L is smaller than S. And if alpha 1 equal to beta 1, then we consider the following. The first variable was t1, and the following is t2. So we consider the powers of t2. Here it is alpha 2 in L, and we have t2 in power beta 2 in S. And so if alpha 1 equal to beta 1, we just say that if alpha 2 bigger than beta 2, then L is bigger than S. If alpha 2 smaller than beta 2, then L is smaller than S, and if alpha 2 equal to beta 2, then so we consider alpha 3 and beta 3 and so on. Either we have in k step that alpha k bigger than beta k, or beta k bigger than alpha k, or all alphas are equal to all betas, then S is equal to L. So for every two monomial S and L, we can say that either S bigger than L, or L bigger than S, or they just coincide. Okay, this is just reminding of the definition. And let us begin with the first task. The first task is just we consider the monomial x squared multiplied by y. Okay, monomial x squared multiplied by y. And we have two ordering. The first is lex xy, and the second is lex yx. So lex xy, and the second is lex yx. And we should say we should describe all monomials that are strictly smaller than this fixed monomial with respect to both orders. Okay, let us begin with the first ordering, lex xy. What monomials are smaller than x squared y? Can you just give me some examples?
XY.
For example, xy. Why it is smaller? Because xy is x in the first, y in the first. And this is x in the second, y in the first. And first of all, we choose x and say that 2 is bigger than 1, then xy is smaller than x squared y. Okay, some more, please.
X square, I guess.
For example, x squared. Okay, we have some examples, and maybe now we can say what is the view of all monomials which are smaller than x squared y.
Well, it's
Yes, please.
no,
Well,
not sure. Well,
X
it's x1 and any degree of y, and
X.
yes, and that's it. And xy without any y, and
X
x
squared
squared
y.
without any y.
And one more kind of this one
And
more.
y, any degree of y.
And the y in k. Okay. This is all monomials which are smaller than x squared y in the first order. Because if we have x in power bigger than 2, then this monomial bigger than x squared y. So these are all monomials with x in power smaller than 2, and so finally we can say that x squared multiplied by y in some power smaller than x squared y just when y is absent. Okay, and now the first, the second order, this one, lex yx. What kind of monomials are smaller than our monomial in the second ordering. In the second ordering, we first of all look at the power of y, and if they are equal, then we look at the power of x. Okay. Can
X
Yx.
in any power.
Yes, x in any power and xy.
x in any power and x y. X y and y. Yes.
True.
Because y cannot be in power bigger than 1. If 1 in the 0 power, then we have the first type. If 1 is the y in power 1, then these two is okay. But if x in more than 2, then the monomial big. Okay, this is just a very simple task to consider definition. Okay, and the second. Find all monomials in two variables, x and y, such there are only finitely many monomials that are smaller than given. We have a monomial m, and we have lexicography ordering lex x y. So we want to describe all monomials m such that there are just finitely many m prime such that m prime is smaller than m. This is also a rather simple problem. Do you have some examples of such monomials m? It seems that, for example, the monomial y squared is good. What are the monomials which are smaller than y squared?
There is an infinite amount of smaller, no? Like x in any power.
No, we have lex
Oh yeah, I
x,
see, I
y.
see. Mhm.
So just first of all, we consider the power of x, and here is x in the 0 power. So if this monomial is bigger than x in k, y in L, then 0 is bigger or equal than k, and so k is equal to 0. And then 2 is bigger than L, so the only monomial which are smaller than y squared is y. We can also say that 1 is a monomial which is equal to x in the 0, y in the 0 power. So there are two monomials, this and this, which are smaller than y in power 2. But that's all. Okay, and if I have, for example, x, how many monomials smaller than x?
Infinitely many.
Infinitely many. What is the view of these monomials?
Y and k.
Y to any, yes.
Why in any power? Yes. If we have a monomial x in some power a or y in power b, then if a not equal to 0, then of course all the monomials y in power k are smaller. So there are infinitely many monomials which are smaller than this one. And the only case is a equal to 0. So we have y in power b. And then all the monomials which are smaller than this are y in b minus 1, and so on, y in 0, which is 1. And there are finite number of these monomials. So the answer to our problem is y in power b. Okay? Oh, sorry. Okay, number 3. Give an example of two monomials in 3 variables such that the first one is strictly smaller than the second one for any lexicography order on the monomials. How many lexicography orders are in monomials in 3 variables?
3.
Not 3.
You mean 9? Is it? No,
But
it's
it's 6.
like 6.
Yes,
Yes, 6.
yes. 3 factorial.
Because we can say that x is bigger than y is bigger than z, x is bigger than y, I'm sorry, is bigger than z is bigger than y. No, there are 6 possibilities to order this x, y, and z. Y is bigger than x is bigger than z. Z is bigger. I'm sorry. Y is bigger than z is bigger than x, and z is bigger than x is bigger than y, and z is bigger than y is bigger than x. So we have 6 orders, but we want 2 monomials such that the first is always smaller than the second. Okay, just give me this example.
Can't we get like x in power a, y in b, and z in c, and the second one is the same, but a plus 1, b plus 1, c plus 1?
Of course, it's correct. Sorry. X in power a plus 1, y in power b plus 1, and z in power c plus 1. And of course, the second is bigger than first in any ordering because just there is, oh, I'm sorry, here is y. There is some variable which is the first, for example, I don't know, y, and then we we look at these powers, b and b plus 1, and of course b plus 1 is bigger. No, for example, x, y, z is always smaller than x squared, y squared, z squared. Okay, and this monomial, which is x in 0, y in 0, z in 0, this is always the smallest monomial among all the monomials. Okay, good. Number 4. We have lexicography ordering, the standard lexicography ordering in ring of polynomials in four variables, and we have these polynomials. Just let me remind what is the remainder and what are the reductions. If we have a polynomial f and a polynomial g, f is the sum of some monomials. I'm sorry. Sorry, just a moment. Да. Да, можно я вам через час перезвоню? Да. Хорошо, спасибо. Спасибо. I'm sorry. We have f is the sum of some monomials m with some coefficients, and okay, we need to define the biggest term, the leading term. What is the denotation of the leading term in your lecture course? This one. Have you some denotation for the leading form of polynomial f? Okay.
I don't remember such a thing.
What's the leading form?
We say that this is leading form is if just is equal to, for example, a multiplied by m, if m is bigger than all other monomials which are in polynomial f with non-zero coefficients. For example, let us just take f is 2x or 3 pi. Okay, what is the leading term of this polynomial f?
The last one, I guess.
The last one.
Yes, the last one, 3 multiplied by x in the fourth, y in the second, and z. Because of, first of all, we consider these powers, 3, 4, 1 here, and 4. So 4 is bigger than 3 and 1, so these two are not correct. So and 4, these two powers are equal, and then we consider the power of y. Here is 1 and here is 2. 2 is bigger, so this is the leading term. Okay, and now we have two polynomials, f and g, and leading term of the polynomial g is some monomial m with some coefficient a. And f is the sum of some monomials, and there is no, there is a monomial b multiplied by m prime, and this m prime is divisible by m. The condition that m prime is divisible by m is the condition that all powers in m prime are not smaller than all powers of m. Okay, then we say that m prime equals to m multiplied by m double prime. Then we say that the reduction of f by polynomial g in this place, in this element, we say that this equal to f minus b divided by a multiplied by m double prime multiplied by g. What is the reason to consider this coefficient? Because here is b multiplied by m, and here is the leading term a multiplied by m. Here is b multiplied by m prime. But when we have a product of this and this, it should be equal to m multiplied by m prime, and these terms annihilate each other, so we can concrete these two terms, and we have a polynomial f without this term and with some smaller terms, because this is here is this is the leading term of the polynomial g. And if we have some a polynomial f and some system g1, gk, we can take f and take a reduction in some order g1, g2, maybe one more time g1, and so on. And then we obtain the polynomial r, which cannot be reduced with any of polynomial g1 and so on gk. Then r is the remainder of f with respect to this system g1 gk. Okay, let us start with our number 4, task number 4. We have f is equal to, sorry, y z squared w, y z squared w minus x z w squared the polynomial g, g1. The polynomial g1 is x plus y. And the polynomial g2 is z plus y. And we want to find a remainder of f with respect to this system of G1 and G2. Let me remind that the remainder can be not unique, but it is not a problem. Okay, first of all, we want to say which terms are leading terms of G1 and G2. What is the leading form of G1? Leading term of G1. We have two terms in G1, X and Y. Let me say that we want to consider lexicography ordering X, Y, Z, W. So with respect to this ordering, the leading term of G1 is X. And the leading term of G2 is, of course, Z. Okay, then we want to take a polynomial in F, which is divisible by sum of one of these terms. Okay, it's your choice. Which monomial, the first or the second in F, I will take, and which of these two guys, X or Z?
What do you mean it's up to us?
Yes, it's up to us. We want to take a term in polynomial f, which is divisible by one of these guys, just leading term of G1 or leading term of G2. There are three possibilities. We take this one. This is divisible by Z. Okay, we can choose this pair. We can take this one, which is divisible by X, and we can take this one, which is divisible by Z. So there are three possibilities for the first reduction. The only possibility which cannot be is this is not divisible by this. Okay, just choose which one is more.
So there are multiple reduction for one polynomial.
Yes, we have
Okay.
this one. We have f. Then we can give some reduction. Maybe then some reduction go to one remainder, but maybe some other reductions goes to the other reminders. I don't know. But we need to obtain just one of these reminders. So the first reduction is up to us. Okay, let me consider, for example, this is polynomial, this is the monomial, and this it is divisible by this guy. Then I say that this is M, and I say that M is equal to Z, this one, multiplied by, of course, Y, Z, W. Okay, and then just by this formula, this one, I need say that f prime equals to f minus minus what? YZW multiplied by G2. this is the leading term of G2. And then F, we have a reduction of F to F1 by polynomial G2. Okay, let us just compute what is the F1. F1 is y z squared w minus x z w squared minus y z w multiplied by z plus w. And we have this guy equals to minus this guy. And this is the rule that this monomial m should vanish by this reduction. So this equal to minus x z w squared minus y z w squared. Okay, this is the first result, and then I must to think, can I reduce this polynomial by my system, these two guys. Okay, if I have a term in my polynomial which is divisible by x or by z. Yes, I have so. So I can reduce this guy, but I need to go to the second frame. So I have the polynomial f1, which is equal to minus x z w squared minus x z w squared minus y z w squared. And I have two polynomials, g1, which is equal to x plus y, and g2, which is equal to z plus w. Okay, the leading terms here are x and z. So let us proceed. We want to choose a term here in f1, which is divisible by x or by z. So let me say, for example, that this term is divisible by x. So I want to reduce the polynomial f1 by the polynomial g1. I say that this guy is m, and m equals to x multiplied by minus z w squared. So I reduce f to f1 to f1 minus minus z w squared multiplied by g1. Okay, this is minus x z w squared minus y z w squared minus, this is plus, because there are two minuses, plus x z w squared and plus y z w squared. And I obtain just 0 here. This is 0. Of course, if I have 0 polynomial, then this is a reminder, because 0 cannot be reduced by any polynomial. So we have f. We reduced it by g2 to polynomial f1, and then we reduced it by g1 to the polynomial f2, which is equal to 0. So this is the remainder. Is it clear how to obtain the remainder? What is the reductions?
Kinda.
Okay, it's very vital to understand what the reductions are. Okay, and now let us go to the number 5. Number 5, we have polynomials in 2 variables with lexicographic order lex xy, and we want to show that the remainder is not unique. Okay, let us show. We have a polynomial x squared f equal to x y squared minus x. And we have a polynomial g equal to x y plus 1. This should be g1. And the second is y squared minus 1. This is g2. Okay, we have a system of 2 polynomials, and we have this polynomial, and we want to find 2 different remainders. First of all, always we compute the leading terms. What is the leading term of g1? Of course, it is not 1, it is xy. So the leading term of g1 is xy. What is the leading term of g2? Again, it is of course not minus 1, it is just y squared. Okay, now we need to start by reduction, which is when we reduct, we choose one of the terms of f, which is divisible by one of the leading forms of our system. Okay, let us choose just by random. For example, this guy is divisible by the first. This is m, and this is divisible by xy. Okay, we say that m equals to a leading term of g1 multiplied by y. So we reduct f by g1, and we say that it is equal to f minus y multiplied by g1. Okay, this is equal to x y squared minus x, this is f, minus y multiplied by g xy plus 1. So we have minus x minus y. Can we reduct this polynomial minus x minus y once more. Is there some reduction of this polynomial?
No, we can
Oh.
divide any term by either of the leadings.
Yes, of course. So this is one of the reminders. So this is reminder. Okay, and now to show that we have not unique possibility of reminder, we need to choose some other way of reductions, and we need to go to some other reminder. Let's try. It seems that x cannot be reduced by any guys, because x is not divisible by xy and x is not divisible by y squared. But this monomial m cannot be reduced by g2. Okay, we say that this monomial m, which is x y squared, is equal to y squared. Y squared is leading term of g1 multiplied by I'm sorry, g2 multiplied by x. So we can reduct f by g2 and obtain f minus x multiplied by g2. So we say that it is x y squared minus x multiplied by y squared minus 1. And it is equal to just 0, yes. And this is the other reminder. So this reminder is depend on the way of our reductions. So here we have an example where there are two not equal reminders. Okay, all is clear. Have you some questions? It seems that you haven't. Okay. Let's proceed with number 5. And today is rather simple list of tasks. So I want some of you to proceed. Let me just write down all the polynomials. F is x squared multiplied by y plus x multiplied by y squared. Okay, plus y squared. And we have two polynomials, xy minus 1. This is g1. And a polynomial y squared minus 1. This is g2. Maybe somebody have possibility to write on this board, not by your mouse, but in some more convenient way. Is there a person which have possibility to write on this board? Unfortunately, it seems that there is no such person. Okay, let me write, and you just say what shall I write. Let us start. We want the task is the same. We want to show that a reminder of S is not unique. Just we need to reduct this F by this system until we obtain reminders. Okay.
No, let's reduce f by g1
Okay, let us reduce F by G1.
and take
So,
the first term as m.
this term is M, and we say that M is equal to what? The leading term of G1 is XY, yes?
For sure.
Okay, this is X multiplied by XY. And what shall I write here?
It's f minus x by g1.
Yes, of course. So it's rather standard. So let me compute x squared y plus x y squared plus y squared minus x square y and minus x. And these are two monomials which we can contract.
Isn't it plus x?
Plus x. Oh, I'm sorry. Yes, of course, plus x. So, and we obtain the polynomial f1, which is x y squared plus y squared plus x. So, can we reduct this polynomial f1?
We can do it by g1 again.
By g1 again. And what term? The first one, yes? This one. Okay, and we say that if it is m prime, then m prime equals to leading term of g1 multiplied by y. Okay, and here I write f minus y multiplied g1.
Isn't it f1 minus?
Of course, f1. Yes. Here is x y squared plus y plus x minus
Plus y squared.
yes, thank you very much, plus y squared minus x y squared plus y. This is the same, we can create, and so this is y squared plus x plus y, and this is f second. Okay, and is there a possibility to reduct f2?
Yeah, by g2.
It seems yes. By g2, yes. We have this guy, which is divisible by leading form of g2. Of course, since these guys are just coincide, then reduction of g2 is very simple. We reduct it by g2, and we go to just f2 minus g2. And it is equal to x plus y plus 1. And this is the this is a reminder because it cannot be reduced by any polynomial g1 or g2. So this is the first reminder R1. And now we need to choose other way of reduction to obtain some other reminder. Let me just write down this in the second frame. X squared y plus xy squared plus y. And we have two polynomials xy minus 1 this is g1 and a polynomial g2 which is equal to y squared minus 1 and this is f. Okay, let us start in some other way different from this. What shall I do in other way?
What if we take, for example, f1, this one, and reduce it by g2, but not by g1? Is it possible?
You want to do the same first step, yes?
Yes, yes.
Okay, we go from F to F1 by the same step, the reduction by G1, and F1 is equal to, let me see, xy squared plus y squared plus x. Okay, and then we reducted f first by g first, and you want to reduct f1 by g2, yes?
Yes, yes.
Yes, we can do it. We have two possibilities. Or this term. They are both is divisible by the leading form of G2, which is here. Okay, let us do first of all the first term, and then we reduct the second term. Formally, this is two different reductions. Okay, let us deal with the second guy, which is m equal x y squared, and this m is equal to leading term of g2 multiplied by x. So we go to f1 minus x multiplied by g2. This is equal to xy squared plus y squared plus x minus xy squared plus x. And this is y squared plus 2x. And then this is f2, and we want to reduct f2 by we can't reduct f2 by g1. We can reduct only by g2. This is the term which is divisible by y squared. They are just coincide, so we obtain f the second minus g2, and this is equal to 2x plus 1. Okay, this is the reminder. And this is a, uh, a different from this reminder. So we have at least two reminders, and it is not unique. Okay. Let me just say that when we have two terms in our polynomial, for example, here, two terms are divisible by the leading form, then you can reduct by G2 using this guy or using this guy. And these are two possibilities by reducting of this polynomial by G2. Okay, то есть sometimes we have a polynomial f, and we can reduct it in many ways. For example, by G1, by G2, and maybe by G1 also, but using other term. It's possible. Okay, and the last one, we have two polynomials in n variables, and f is divisible by g. Please prove that for any lexicography order, f is reducible to 0 by g. Okay. We have two polynomials, f and g, in some field and n variables. And we know that f is divisible by g. So we want to take f, we obtain, I don't know, some reductions, and we say that we must to go to 0 reminder. In any lex, maybe x, y1, x, I2, and so on. Okay, can somebody say something to prove this fact? Let us think about it just during 3 minutes.
So f and g are polynomials, right?
Please say it one more.
F and g are polynomials, right?
Yes, f and g are polynomials, yes.
Yeah.
Let me give an example. For example, if I have f equal to x plus y, for example, multiple by x minus y, which is equal to, of course, x squared minus y squared, and g is equal to x plus y. Then I take f, and the leading term of g depend on our order, but let me take, for example, x, y. Then g, the leading term of g is x, and I reduct f by g. I say that it should be x squared minus y squared minus x, because x squared equal to x multiplied by x multiplied by g. And this is minus y squared minus xy. This term is divisible by x, so I can say that it is f1. F1 can be reduced by g, and I obtain minus y squared minus xy minus y multiplied by g, and this is just 0. So this is an example which show that x can be reduced by g to 0. But our task to understand why always f can be reduced by g to 0. So f should have the unique remainder, which is 0. Okay, let us begin. I just suggest to prove by induction in some sense by induction. Induction in L of f. Let us consider the unique one of the reduction. So we have a polynomial f, and we reduct it by the polynomial g. I'm sorry. Okay, let us think about it. We have f, and we reduct it by g. So we obtain a polynomial f1, which is equal to f minus some guy, I don't know, coefficient c monomial m prime multiplied by g. What can I know that f is divisible by g. What about f1?
It's also divisible by g, I guess.
Of course, it's also divisible by g, because the difference between f and f1 is this one, which is divisible by g. So if I take f and I reduct it by g, here all the results are divisible by G. Okay, but if I have let me suppose that I have F, I reduct it by G, then I also reduct it by G, and so on, and I obtain a remainder R. What can I say about remainder R? Of course, this remainder is divisible by G. Because all these guys are divisible by G. But if this remainder is divisible by G, then of course this is not remainder, because what can I say about leading term of this remainder? Of course, it is divisible by the leading term of G. And since it is divisible by the leading term of G, then I can reduct it by G. So this is not remainder. I can proceed with this guy and obtain some other remainder. So if I have a remainder which is divisible by G, the only possibility of this remainder is to be 0, because if it is not equal to 0, I can reduct it one more time. Is it clear?
Yes.
And this is not depend on our ordering. Of course, in any ordering, this proof is correct. And the only problem, maybe the only gap, is that we should go to a remainder. But it seems that in your lecture course, you understood that every polynomial f with every system of monomials G1, G2, and so on, Gk, goes to a remainder. So you cannot reduct infinitely many times. You just go to a remainder, because the leading form, the leading term became smaller, and there is no infinite it couldn't be became smaller infinite times. Okay, it seems that today all is good, because we understand the solutions of all the tasks. Do you have some questions?
Yeah, I've got one question. In the homework,
please.
in the number 4, what does the lexicographical order coincides with the ordering by degree mean if there is only one variable?
Let me see. Number 4, yes. We have this one. The lexicographical order coincides with the ordering by degree. Okay, of course, because if you have just one variable, then what is the ordering? We just
Oh, so we just say that the leading element
say
is the
that-
element with the biggest power, right?
of course, yeah,
Oh, okay, I see. Then it's
X
obvious.
and k bigger than L is k, if and only if k is bigger than L. This is just by this power. Yes. Okay, you understand, yes?
Yeah, then it's obvious. I see.
Okay, maybe some more questions? So I have a question. You have a seminar in linear algebra after this, yes?
Yep.
So I can't do the I don't know in English consultation. Yes, we have a consultation in this time, but no, today it's not possible. So if you want a consultation, I can do it, for example, in Thursday. So if you want it, then just write to my email, and in Thursday evening, I think it's a good place for a consultation. Okay, then thank you very much. If you have not questions, then thank you.
Okay, thank you. Bye.
Thank you.
Goodbye.
Bye.
Thank you.
And I remind that in Friday you have a deadline for the previous homework.